welcome. So this is our second PID control webinar in the series of 3. So the first session, we had a lot of discussion regarding the operation of the PID definitions, principles, and a lot of terms that were discussed on all the elements that relates to PID control. And also we had a small demonstration at the end of already compiled PID control project, just to demonstrate some of the key concepts we had there. For this presentation, we'll be looking at more in-depth concepts regarding the operation of the PID itself, okay? As well as we will have a more detailed demonstration in the sense of how to start a PID project from scratch. And as an extra bonus, we will just connect to the GT Simulator as well, just to show how that has been set up just for the simulation and testing purposes of this concept. Then for the third part, which will be the final presentation for PID control, we'll be looking at all the fine-tuning options, auto-tuning options, as well as how to utilize the function block diagrams and data types for efficient PID control. So if we look at the schedule for today, okay, so we will have two parts. So the first part will be just a rough quick discussion on all of the mathematical concepts of the PID. So we'll look at each one of the controller gains, and then also the mathematics behind the control actions. So the forward control versus the reverse control actions of PID, okay? And then we'll have a practical demonstration just to show how one would start a small PID project in GX Works3. And then also we will use the simulators to link to GT Works, just to make a nice simulation of feedback of data and the control rates and so on. Right. So as I mentioned in the first part, there's a gap between the theoretical PID control, how can I say, magisteria, and the practical implementation in the field. Okay, so the purpose of these webinars is to try and bridge that gap. Okay, so on the theory side, there's a lot of mathematics and calculations and formula derivations and so on. But we will try to keep that as minimum as possible and only cover the most important mathematical concepts specific to practical PID control in the field. So the aim is to bring understanding to the formulas that's being used within the PID block. Okay, so that will be the first part. Yeah, the second part, obviously, like I said, will be a dual demonstration, GT Works and GX Works, just to show the concept and the operation, how to configure a PID and so on. Okay, so so in GX Works3, we've got a couple of PID function block types. This one, which I have here on the screen, is the most popular one, okay, and the most powerful one. And we will be building one of these at the end of this present webinar. So the first part of this presentation, we're going to see how this PID block works. So what's underneath, what's happening inside, how does it make decisions on achieving optimum efficient control in the field. Okay, there's, like I said, there's a lot of maths inside. Is it necessarily a requirement to understand all of the maths inside of the PID block? No, not at all. But will it help you to understand a PID in terms of configuration, programming, fine-tuning, and so on? Absolutely. Okay. So if there's Mathematics is absolutely not a requirement to use this block. Anybody can use this block. It's just a simple procedure to be followed, and then you should be good in your application. Right. So as I mentioned in the first section, the purpose of PID control, or the principle of operation, is to mitigate the error. Okay, so the error is defined as the difference between a set point, aka what the user wants the process to be in terms of temperature, level, flow rate, or whatever. And obviously the process variable is the actual measured value of the process, temperature, flow rate, level, whatever. Okay. And the difference between those two variables will be your error. Okay. So as long as your error is 0, your PID block will be happy and your the objectives are achieved. Okay. Now there are a couple methods in achieving this objective, and we'll be discussing that throughout this webinar. So we're using closed loop control for PID. Now, actually recall from part 1, closed loop control is a control system that monitors the output via a feedback signal. Okay, and that feedback signal is a representation of the process variable. So just keep in mind that in some of the OEMs or vendors or books or courses that we will attend in the future or attended, they will use different terminology. So that's why I included the feedback value variable here as well, just to understand where it fits in. Okay, so your error will go to 0 the closer your process variable reaches your set point. So that is the core principle and objective of a PID control block. Okay. So if you put all of that together and you want to create a philosophy, so it means that the error, if the error is larger than 0, then it means your set point is larger than the process variable. Error is 0, that means that your set point and your process variable are equal, and which means your objective is achieved. And then obviously, if your process variable is larger than the set point, then your error will be smaller than 0. So which means the error can be negative and positive. That is a takeaway here. Very important. These signs, greater than and equal and larger than, okay, smaller than, will swap around depending on your PID action, whether you have a reverse control action or a forward control action. An easy way to understand that is if you have let's for instance have a tank level, and the tank level you control with, let's say, a valve or a VFD which controls a pump or motor. Okay, if the valve or the VFD fills the tank, okay, then obviously if the tank level goes too high, then the speed will slow down of the VFD, or the valve will close. It's a valve. So that would be a reverse control action. If the valve sits underneath the tank, or the VFD pumps the fluid out of the tank, then that would be a forward control PID. Okay, so just those two factors to keep in mind, and we'll be discussing that at the end as well. Right. So in short, the PID, like we mentioned, it's got 3 terms: P term, I term, and D term. That is the 3 terms the PID uses to achieve its goal of 0 error. Okay. And each one of those terms have a specific function, and not all of them need to be used. Some of them can be excluded depending on the application. Okay, so that's something to keep in mind there. So your P term, that is your proportional term. So there's the formula representation. So so that the KP there would be your proportional gain. ET will be your error. Your I term will be your integral multiplied by the integration of the error over time, definite time. Okay, so this will look at the historical error. Okay, and then your D term, this should be your D term, looks at the future. Okay, and that will be your D gain. Okay, so it looks at your rate of change. So we did discuss this in part 1, for those who want to refer back to that as a reference later on. Okay, so if you add all of that together, that is your formula for PID control. Okay. That is included in your PID function block. So many users try to avoid PID control because they look at these formulas and they get discouraged in the sense of either they need to understand the formulas, how they work, or they think that they will have active input in the formula in the sense of the back end of the PID. So none of those are the case. All of this happens inside of the PID block. The only thing that the user needs to define will be the gains and the times, the sampling times and your integral times and so on. The PID block in the PLC will perform this calculation internally, and you don't have to worry about the processes from that point of view. From a signal perspective, what the user needs to provide will be 3 signals. 2 inputs, 1 output. So the 2 inputs would be your set point signal and your process variable signal. Many applications only have 1 input signal, which is your process variable, which means the set point will be set via a HMI, meaning a GOT or a SCADA or another method. As for the outputs, that would be your manipulated value, as we discussed in part 1. That will be connected to your actuator in the field, whether a valve, a VFD, a meter, depending on the application. Okay, so the first part will be your proportional, which it looks at the current error that's happening in a plant. Then the second part will be your integral, which looks at the area under your trend graph, which means historical errors. And then you have your derivative component of the PID control, which looks at rate of change. Therefore, it can predict the error, so it looks at the future. Right. So if you look at the proportional gain quickly, as we mentioned, the proportional looks at the current error. Okay, and it's usually called a control spot fixer. Okay, this is what this P parameter is called in some of the textbooks or training courses that you might attend or will attend. So that control spot fixer will refer to the P parameter or the P factor of the PID control. Okay, so these relationships which you see here, okay, it's easy to it's easy to derive. Okay, so basically your proportional gain. Sorry, we will have questions at the end of the webinar. Okay, just want to run through the theory part here. Okay, so how the P works is the greater your error, the greater your P output. Okay, so that's why I'm saying it's directly proportional. So if the error is small, your P output of the PID control will be small. Okay. If the error is large, then it will react very aggressively. So that's therefore your proportional output is directly proportional to your error. Okay. Now, how does that work to the signals in your plant then? Okay, so if you have your set point, which is, let's say, 100 degrees Celsius, and you've got your process variable, which is, let's say, 90 degrees Celsius, there's obviously an error there, okay? So the larger that error, okay? So the larger this error here, the faster your, more aggressive, your proportional gain will react, okay? So why is this important to understand? Sometimes you will see when you fine-tune a PID controller or function block, you will have a overshoot if your P variable is too high. So which means that your process variable will oscillate very sharply around the set point. So it will go overshoot, undershoot, overshoot, undershoot, and it will always chase that set point, but will never reach it. So this will happen if your P gain is too high. If your P gain is too low, then it means that your process variable will never overshoot. It will your P parameter will never overshoot. It will gradually go towards the set point. But the problem with that is then your set point will never be reached. There will always be error. The error will go smaller with time, but there will always be error. So that's why it's important to have the correct value for your P. Okay, and that will depend on your application in the plant. There's no magic formula to select these gain values. There's only two ways to do that: the fine-tuning trial and error, and obviously the auto-tuning, which is automatic in the PLC. And both of these can also yield, in rare cases, problematic results. Okay, so this is how a P controller will look like. There are a lot of P controllers in the field, which does not incorporate the I parameter or a D parameter at all. So these are for applications that you don't need that level of accuracy. So if you have like a water dam somewhere in the field that you would use for cattle or so on to keep the dam level in control, you wouldn't mind too much of a overshoot or an undershoot as long as there's water in the tank. So that would be a P controller. Okay. However, if you look at highly accurate systems like petrochem applications where tank levels must be precise, then a P controller alone will be insufficient because of the overshoot and undershoot, as well as the steady state error. Okay, so the mathematical formulas, as if we put it in, if we put that relationship in a mathematical layout, so your P factor will be your gain multiplied by your error. So if your error is large, then your controller will react aggressively. If your P gain is large, your controller will react aggressively to the error. Okay, so, and obviously your error will be your set point, which is user defined, minus your process variable, which is the signal you measure from the field. Okay, and then we can just put them together to get the P factor. Right. So as I mentioned, the P gain factor, the P gain element of this formula has a huge effect on your output of your PLC, your VFD or your valve. So if you look at the graph here, this will be a typical case where your P is too aggressive. Your P gain is too high. Your KP value is too high. So what happens will overshoot. It will realize that it's overshooting, and then obviously when the error goes high again, it will try to mitigate that error, and will undershoot again, overshoot, undershoot, until it reaches a steady state. But now notice that you will have a steady state error. It's stable, no more oscillation, but there's a steady state error, which means there will always be a constant error between your set point and your process variable. And that is why a P controller alone is not recommended for applications where high accuracy is required. Okay. So to mitigate this error, we will look at the I controller of the PID controller series. Okay. Just a side note here, in some manuals, books, courses, videos, and so on, they don't refer to KP. They refer to KC as the P controller gain. So if you see a KC in a manual or in a book or in a project scope or so on, then you can be assured that it will be your proportional gain. Okay, so it differs from vendor to vendor and OEM to OEM. Okay. So naturally, if there's zero error, then obviously 0 times your KP, because your error is the formula, 0 times KP will mean that your P controller will not react at all. It's satisfied. The error is 0. So that is the function of this formula there. It's a simple multiplication. So we looked at 2 problems with this proportional gain, which is obviously the oscillation, if your KP is too high, and steady state error if your KP is too low. And your steady state error is in fact inevitable as well, irrespective if your KP gain is high or low. So eventually, if the system settles down, there will be a small error, which is too small for the P controller to pick up. Okay, so those are the two errors that we have for the P controller alone. Okay, so we discussed the overshoot and undershoot. Okay, and when the convergence is reached, in other words, it's stabilized, then you'll have your steady state error. So, and this is the effect of only. Okay, so this is the effect if you only look at the current error. You don't look at the historical error, and you don't look at the future error, your rate of change error. So the future error will mitigate your overshoot and undershoots because it looks at the rate of change of the error. And your historical error will look at your steady state error, the historical factor, which is your I controller. So as that steady state error increases in time, it will try to reduce that value. So that's where the I controller comes in. Yeah. So just now demonstration of what we discussed earlier regarding the overshoot and undershoot. If your gains for your proportional controller is too high, if it's too low because you don't want overshoot, then it will never reach your set point practically. Theoretically, it will after a very long time, but practically it will never reach it. So that's something to keep in mind when selecting a KP gain. Right, to conclude the proportional controllers part, okay, so we only look at current instantaneous errors, and it's very ineffective for small errors, okay, which comes in the form of your steady state error. So all of these problems which we identified can now be addressed with the I controller, as mentioned. Okay, so the I controller looks at small errors over time and will fine tune or will finalize the error correction to reach a zero error. Okay. The reason for that is it accumulates the error over time, and obviously as the error accumulates, the higher the error and the more aggressive the integral controller will react to it. Just a reminder that this error can be both negative or positive, depending if you have got a forward control or a reverse control application in the field. And therefore, this error will be the absolute value of the error. So it doesn't matter if it's a negative error or a positive error, any error is seen as bad and will be addressed by your control parameters. Okay. So the I controller cannot be used alone. It needs to be used with a proportional controller. Okay. So therefore you will have a PI controller, which is in fact the most popular controller in the world. Okay. The second most popular will be your PID controller. The third will be your P controller, and then there's in very, very rare cases you'll have a PD controller, and that would be usually for automation in motion and so on. We have servo motors, but even then, in most of those cases, you'll use a PID, not just a PD. But okay, so the problem with the PI controller is that it's not very, it slows down the process controller. Okay, so because it looks at the steady state error that builds up over time. So the more time you give it, the more accurately it will control the process, but it's very time dependent. So if you don't give it enough time to calculate the error with a I controller, then it will also not yield the required results with your steady state error. Okay, so how do we put all of this in a simplified way to understand how the I controller works? So the I controller can be seen as a bucket or a container. which has small, it accumulates small errors like drops of water. And obviously, the longer you allow that bucket to fill, obviously, the more water will be in that bucket, and therefore it will react faster, get that bucket empty. Okay, so that's how our eye controller works. A P controller will not see the drops of water in the bucket because it doesn't look at small changes. It looks at aggressive, large errors. Okay, so the purpose of the integral controller will be to keep that accumulation container empty. Okay, whilst the P controller will look at the more larger, more aggressive errors that's experienced in the plant. Okay, so we can see that the eye controller uses the function T, and that's in that case it uses time, which slows down the control system, but gives a more accurate control. Okay. The principle of operation of the eye controller will be the definite integration over time. If you look at it from a mathematical sense, if you look at it from an industrial application sense, like PLC programming, so on, that would be can be best compared to a totalizer. Okay, a totalizer that resets over time. Okay, so just want to see, okay, so we discussed this part here. We said it's a function of the time. Yeah, that's perfect. Okay, so there's the mathematical formula for the eye controller. Okay, so as I mentioned, it uses the integration function, and it uses the integration of a function. In this case, the function is the error. So it would accumulate all of the errors over a set of time, and will control the VFD or valve or heater or whatever actuator is in that regard. So to simplify it for any person who are not familiar with any mathematical principles here, when you see a integral sign, what it means is it looks at the error on a graph, the area underneath a graph. So the larger the area, the larger this value will be. Okay, so it's basically just to see the error, which we'll see in a trend graph, the difference between your set point and the first variable. That would be your eye controller's function to reduce that. Okay, so so no need to perform any mathematical calculations. That is the PLC's job. Right. So as I mentioned, it will affect your response rate. So the speed of response, which would reduce your actuator's output response rate, but it will stabilize your control system. Okay. So it's important to have a balance between stability and accuracy. These two functions, these two factors, work against each other. Okay, so that's why you have to have a perfect balance depending on your application. Okay, so if you want something that's very accurate, it will be slow. If you want something that's very active in reacting to errors, it will give inaccuracies due to overshoot and undershoot and steady state errors. So a balance needs to be achieved there to give the best error correction over time. Okay. So that means that your response rate is indirectly proportional to your gain. So the larger your gain, the smaller your response rate. Okay, which means your response time will be high. Okay. Now, on the other hand, the larger your steady state error, okay, means that you've got a very small gain for your integral controller. So that's what I'm saying. A balance needs to be achieved. Okay, so either you have a very aggressive reaction system or a very slow system, but accurate. Yeah. So if you add the integral controller factor to your control system, your closed loop control system, then it would be this element here. Okay, so this time, integral time, is indirectly proportional to your gain. As you can see, it's a 1 over pi. So it's the opposite of that value. Just to be clear, this is a control loop, closed loop control system. This process variable here would be the output from the plant, which comes back as a feedback signal for measurement of the errors. Right, so from a graph point of view, so now we've got two elements. We've got your P gain and you've got your I gain. So just a couple of examples, theoretical examples of how these gains will affect the error. Okay, so if you introduce a step input on your process, obviously if you've got a very high gain, you will have an overshoot. Okay, and if you have a high integral gain, it would drastically decrease the error. This area underneath the graph here would be the error in a stable fashion until the steady state error is reached. On the other hand, if your gain for your proportional controller is low, then it would overshoot little, and in some cases it will never reach the set point. It will just settle underneath the set point value, and then your integral gain will now do the rest to stabilize the signal and to reduce the error to 0. If your integral gain is sufficiently high enough. If it's too low, then it will take some time to reach that 0 error. Right. So here's another example with only the integral gains. If you exclude the proportional gains, so if the integral gain is too low, then too high, then we will have undershoot. If it's too low, we'll have overshoot. So we need to get a balanced gain for your integral controller. I just want to point out something. We call this TI gain, but it's in actual fact not the gain. KI is the gain, but TI is one of the variables that needs to be defined when you configure your PID block in GX Works3 and obviously in other controllers as well. So that's why we call this, for simplicity's sake, a gain as well, but it's not. Mathematically, it's just a time period. Okay. Right, so to conclude the I controller, so there's the formula. So it will look at the total gain, okay, and it will look at the I factor here, okay, and this I factor is calculated as a function of the error and also how fast your PLC samples for new data, and also how high your configuration gain is in the I controller. So if we plug that into that formula, then we see how the PLC would continuously update the I factor control, I factor output by looking continuously at the error over a cycle of time with the user-defined gain. So in this whole formula, the only input that you as the user will have will be this I gain here, okay, where you will configure it. The error will be calculated internally in the PLC, and obviously the cycle period will be configured on the PLC. It will also depend on what PLC you have. It will also depend on your hardware in the field, if they can handle high sampling rates and high outputs. And so this cycle period will be hardware dependent, and this error will be dependent on your performance of your controller, and this will be dependent on the user's input on how aggressive he wants the I factor to affect the control system. Right, so just to finalize, so the I controllers looks at the past, the history, and but there's a disadvantage in this controller. It's the disadvantage is that in some cases there will be like a drift where the I controller will not do error correction anymore, even though there's a small error. That's very rare. It's caused by wind up factors in your control system, but this is something to keep in mind And also, if your I is too low, you will get overshoot. So it's just something to keep in mind. Right. So the last element in the controller, the PID controller, is the D controller. Okay. So this is the most rare type of controller, the most rare element in a PID controller. Usually all of them are PI or P, okay? But PID, even though the name suggests it's a common use, it's not the most common used controller. But if you set it right, you have optimum control. Okay, so the D, what it does here, it looks at your rate of change errors. So it will look at your overshoots and undershoots, sharp error correction. Okay. How it does that, it predicts where the error will be in a certain point of time based on the error that you currently have right now. So if it sees an error of, let's say, 5 liters per second, okay, then it means in 3 seconds you'll have a 15 liter error. And that's how the D derivative proactively predicts the error and then proactively try to reduce the error. So if I increase my output of my D term, then it means instead of having a 15 liters error, I'll have a 12 liters error or a 9 liters error. So it will continuously try to do that. Okay, so so 2 factors that will activate the D controller very aggressively would be if the user types in another set point in HMI or SCADA, immediately there will be a very high error. So it would activate the error immediately until the system stabilizes. Another element that can cause a very high D response is if there's a instantaneous error being induced in the plant process. Let's say pipe burst on the tank level, or if it's a very small tank, then your D term will play a huge role to try and reduce the error to 0. Okay. So as I said, the D controller, it counteracts the overshoot. And if there's a very large error, then it will push the controller will push a very powerful output, analog output to the actuators to mitigate that error aggressively. That is something that the P and PI controllers don't have. Okay, but in many applications don't need them, but in some applications you do need it. Okay, so the advantage of the D controller is if you have a D controller in your PID control system, and you've got a quite high gain there, it means that now you can go back to P and I controllers and increase them as well, because now you don't have to worry so much about overshoot or undershoot, because the D controller is it also acts as a damper, so it has damping effects on the PNI and PI controllers outputs, so it can mitigate those errors as well. Okay, so it's just something to keep in mind. Right, so as I mentioned, it looks at rate of change, which it looks at the current error subtracting the previous error over the measuring period, and then you get your delta error here. So delta is your change of the error, which means it's your rate of change of an analog signal. So if your delta is high, it means your rate of change is high. So that's what it looks like. That's what it uses to control the output of the D10. Right. As I mentioned, the D controller is rare, and it's also the most complex of controllers, because now the fine-tuning needs to take into account 3 factors. So instead of balancing 2 factors, which is your P and I, you have to now balance 3 factors. You have to look at your rate of change as well. Okay, but for cases where the error needs to be kept to 0 very aggressively, very fast, you will have to have a very high D term controller. Okay, so the purpose of the D controller is for proactive control. high-speed control, and for anticipation of future errors. So theoretically, it's recommended to have a decontroller in all of your control systems, theoretically. The problem comes in practically when you have a signal, a very long signal that uses, let's say, 0 to 10 volts, or a cable that is not shielded with a foiled. So there's an area where there's a lot of electromagnetic noise, like cables that run with HD cables or so on, where there's a lot of magnetic induction in cables. You will get inaccurate analog values. Okay, and your derivative controller will see that as a actual error in the field. You'll see that those signals are the actual signals in the field, and will react very aggressively to all these magnetic inductions of your interference or noise which you get in the cable. It won't distinguish between what's actually happening in the plant and interference on the cable. So every spike you get on a milliamp signal, on a voltage signal, or a milliamp signal which doesn't run on a foiled cable, a shielded cable, will be seen as an error in your tank. Like it will see that the tank level is overflowing or it's running empty. So it will very aggressively try to stabilize that. And as we know, the PID controller cannot stabilize anything on signal cables, noise that's inducted in the signal cables. So you will have a lot of oscillations in the plant and unstable control system. And as we know, unstable control system will overwork the actuators, like your heaters will cool down and heat up very fast. But continuously, your valves will continuously open and close, your control valves. Or your VFD will constantly ramp up, ramp down, ramp up, ramp down all the time, which means the motor accelerates and decelerates and will affect the currents in the coils and reduce your lifetime of your hardware due to currents and so on, heat that's induced. So that's why my point I'm trying to make is if you use a derivative control and you want to use a very high D-term gain, KD, make sure that there's no noise on the cable. Make sure your cables are grounded and they're shielded and doesn't run next to HD cables. Preferably milliamps over voltage, 0 to 10 volts, because milliamps is less affected, but it is still affected. So just something to look at in the derivative control. So if you have an application in plant where there's continuous oscillations and ramps up and ramp downs, then it might be something wrong on your D controller. If you are required to have a D controller in your plant, but there's also an element of noise, the only way you can address that problem, other than install shielded foiled cables, is to reduce your derivative gain KD very small. Okay, so then you will have a less powerful control system, but it will not react to noise that aggressively. If you have a very noisy area and you don't need the KD term, if you remove the KD term, then you will see that your control system will be more stable. I want to point out that these mitigation measures which we discussed now obviously will not address the root cause of the problem, which is induction in the cable, noise induction in cable, which is due to HD cables or incorrect installation practices or unshielded incorrect cables used, or the distance of the cables is too long and so on. So it's recommended that that will be addressed first. Okay, right. So so if we include this derivative gain factor into the PID control system, as you can see there, we added it there, and it's also a factor of time, but this time it's proportional with time, so it reacts very fast. So the longer the time, the more aggressive it will react. Yeah. So this will be the 3 factors that's included in a PID controller to give you your output circuit, your P term, I term, and your D term that's used. Right. So we look here at this example here. If you add a D term here, okay, now the steady state error falls away completely as well, and the PLC will be very sensitive to small errors being induced. So the controller will immediately react to small errors, and therefore you will reach your desired set point in this step root function here. So the point I'm trying to make here is that the higher your D controller, the more aggressively you can increase your I and P gains, and therefore you can have a system that settles faster. By settling, I mean with a zero error, meaning like here we've got the near zero error with the set point with relation to the process variable. Okay. So in an ideal scenario where there's no noise, your D controller improves your system stability and also your system's reactivity. So it's very reactive. So it's something to take into account. So a problem that this will be solved, if you refer back to your previous slide where I mentioned that you will in some cases have a wind up error if you only have a P and I controller, which is very rare what happens. Then the introduction of a D controller will mitigate that error as well. Okay, for a faster setting time. Why is that? Because introducing a D controller, you can now have a more aggressive I controller, which means it will now more aggressively attack your steady state error, and therefore you will reach your set point much faster. So that is another advantage of including a D controller into your PID control system. Okay, so this controller is also directly proportional, meaning that the higher your gain, the higher your response rate. So if you don't want your PID controller to react too fast, you can lower your D. Now, theoretically, obviously, everybody wants the fastest response rate. The fastest response rate, fastest sampling rate of errors. And theoretically, that's a good thing. Practically, the faster your response rate, the faster your error correction, meaning that the more your actuator will work. So your valve will never reach a point where it will be stable or off for a long period. It will continuously try to chase that error. So that is something to keep into mind if your system is too accurate or too aggressive. Okay. Right, so just the conclusion. So we look at the projected future value by a prediction. That's the D. If you want to predict what the error will be over time and then proactively reduce that error. The disadvantage would be obviously very sensitive. This is the most sensitive controller. So any noise that's induced in the cable will be seen as a drastic error, and the PID controller will react to it very aggressively. And obviously the output of the PID controller will not affect the electromagnetic noise at all. So there's something to keep in mind. Right, so if you put all of these formulas for these controllers together, which we discussed now, so then this is the formula that is used in PID controllers. So many PID controllers uses a slightly different formula. The output will be still the same, the principle is the same, but they do move certain factors around and make small fine-tuning internal to the PLC. But this formula is the generalized accepted formula for general PID control, okay, which will also apply to our demonstration a bit later on. Okay. As I mentioned, PID control actions, so this will be your reverse versus your forward control action of your plant. So example given, are you filling a tank or are you draining a tank? Both can be used for for a PID control. Okay, and difference is you will have a reverse action and forward action depending on the application. Same with cooling and heating. Are you heating a furnace or are you cooling a fridge? Okay, so that will also be dependent on your forward control action or your reverse control action. Okay, a good rule of thumb is if your analog input signal going into your PLC, if it rises and you require the output to reduce, then that would be a reverse control action. If your input from the field, your process variable into the PLC rises and you want your output going to actuator also to rise, then that would be a forward control action. Okay. So how does that apply to a physical practical example of plant? If you have a thermocouple in a furnace, RFD, okay, you will have, and you want the furnace to heat up. So for metal or so on, that would be a a reverse control action. Because if the furnace gets too hot, you want the valves for the combustible gas to start closing. And what will determine if the furnace gets too hot? That would be your feedback signal from your analog signal, which is your thermocouple RD, coming from the furnace into your PLC, which will give you a high analog input into the PLC. So therefore, you have a reverse control action. If you look at a forward control action, let's look at tanks draining. So if you want to fill a tank, okay, and not drain a tank, okay, then you will use a forward control action because you are filling the tank, okay, sorry, reverse control action. If you want to drain the tank, which means that the tank needs to be kept empty, depending on your level which you measure, it would be your forward control action. So once again, how do we determine that? If your PLC's analog output signal needs to increase based on an increase on your input signal from your field, your process variable, then you will need a forward control action. Okay. Otherwise, it will be a reverse control action. Okay. So that is a simple rule that can be followed if you are unsure. However, practically, if many users, they don't know about these control actions. They will configure the PLC PID controller based on trial and error, based on the trial and error and the process variable and how the actuator reacts. So that is the most common method. Okay. So, and I'll show you how to do it in the PLC as well. But if you look at theoretically, the correct way to do this, it will be to take into account your PID control actions. Okay. And this is how the formula inside of the PID control will change based on your selection. Okay. So you can have a negative error or a positive error. Yeah. But okay, so we'll have a quick demonstration on how to configure a simple PID control system. Before I do that, I just want to mention one thing. Practically, PID control systems, they are traditionally set by parameterization. So user parameterization. So you as a user will add the parameters and you will keep an eye on the response time of your control system, and then you will fine tune it accordingly. With the FX5 PLCs, GX Works3, and also the IQR PLCs, and I think some of the more advanced GX Works2 PLCs, your Q series and so on, you can include auto tuning. Yeah. So there are two auto tuning strategies to help you to find the correct gain values for your PID control system. But that is a discipline or a field by its own. And for that, we'll have a separate webinar, part 3, where we will discuss this in detail. So For this application, for this demonstration, we'll just start with the empty GX Works3 program. We'll set the variables, and then we will create a PID block, and then we will set the parameters for this PID block. So all these variables which we discussed here so far is included in these parameters here. So if you have a question, what's the importance of understanding what TI means, or what is the importance of understanding what KP means, or why do you need gains, it will be answered by this section here. Okay, so these are the parameters that you'll put into the PID to tell the PID how to react to certain errors in the plant. Okay. In many cases, the users don't want to know the gains. They don't want to go the mathematical route. Okay, so for that we'll look at the auto tuning methods. This will be the next webinar. Okay, so after we set up all the parameter coefficients and we initiated PLC PID control, then we will just include that in just a small demonstration on the GOT, so we can simulate inputs and outputs and see how the PLC respond to the errors. Okay, so it's this demonstration is serves a dual purpose. It shows you how to link the two simulators together, GT Works and GX Works, and it also will demonstrate some of these concepts which we discussed now, very basically. Okay, so as I mentioned, these parameters need to be set up by the user or by the PLC if you do auto tuning. If it's done by the user, these are the parameters that need to be kept in mind. For our simple demonstration here, we'll only look at these yellow highlighted ones. Yeah, okay, because it's a very simple application. We're not going to put satellites in orbit here. And if you want to know more about each and every one of these variables here, or if there's some formula that didn't make sense to you, I did include the e-manual viewer page here. So this will be the page number there that you will copy and paste into your e-manual viewer, and then you'll get all of these information in detail. Okay, so let me just open GX Works, then we will go from there. Okay, so I'm just going to start a new project from scratch here. So I'm just going to close here. Okay, so let me open GX Works3. So you'll have your engineering software interface here. So let's just start the new project. You can use FX5 for now. Okay, so I'm just going to make some space here. Right, so we can program this. We can use this area to program our PID controller. So the first thing first is to create the variables. Okay, so just want to add a function block. So this will be the function block. So all that mathematics which we've seen is contained within this function block. So you as an end user or engineer or technician or project specialist don't have to worry about that formulas. All of that's done inside here. Okay, you only need to define the gain variables and the time variables. Okay, so we go to the variables here. So we're just going to create our variable list here. So first things first, we all need to activate or deactivate the control systems. We'll call it the PLC start. Okay, so this will be in cases where you want a PID controller to stop where it is. Let's say it's an emergency or a plant shutdown or whatever the reason might be. If you want the control system to stop, this will be your variable, and this will be a bit type. And since we want to automate the system, so in this case, we don't want the user to be able to change the stop and start the PLC. We only want the user to stop and start a PID controller. So we'll just use the address SM400. So SM400 is the internal special bit that's used in your FX5 PLCs that will turn on automatically. This bit will always turn on if your PLC is running. So if the PLC has got no error and the system's healthy and the power is in place and your program in place, this SM400 will turn on automatically. Okay. Then what other bits do we need? Okay, so as I mentioned, let's say you want to stop and start a PID control process, but keep the PLC running. You'll have a PID start. This will also be a bit. And I'm just going to give it an internal address for now in 100. Can be internal, can be a push button. In other words, can be X address. Can be a signal that comes from a Android SCADA or any SCADA. So if it's an Android SCADA, it can be a D address. If it comes from another PLC in a network, M addresses will be fine. If you want to use an output signal to activate the start, can be a Y address. Okay, so just something to keep in mind. Okay, so what else do we need for a PID controller? Okay, so we'll need the analog input signal coming from the field. Okay, so this would be a set point value. So let's say we call it PID SB, set point. And obviously this would be a word, signed word. Okay, and we'll give it an address. Let's just give it an address of B2. Okay, now if you have a physical analog input card, this will be a SD value. Okay, depending how you configure this analog card. For this demonstration, we don't have a physical analog input signal. You can use simulators. So I use D values. It's just something to keep in mind. If you have a physical analog input card, you will have to use the analog input signal, the address, device address. Okay. Another thing to keep in mind here is if you're using an HMI, like a GOT or a SCADA, you can also use a D address because it means the operator using the SCADA in the plant will set in the set points. So if you have like a potentiometer which sets set point meters, set points, then you have an analog input card. Just as an example. Okay. Now, what else do we need? Oh, we need the process variable. So process variable, what is that again? That is my sensor or transmitter for closed loop feedback, like temperature sensor, RD, thermocouple, or a level probe, anything that measures inputs. Can be motor speed, can be system pressure, anything that measures. So it will also be a word, because it will be integer value or a real value. So we keep it the T0 here, because it's a simulator. And then how is this PLC going to give an output to the PFD or valve or meter or whatever actuator you have? So you have to give it an output as well. So MV, manipulate the value. And this will be a signed word as well. And I'm just going to give it an address here for argument's sake. P4. Once again, if it's an analog output signal, which has a physical card output, then you have a SD special device here, mostly. So you'll have a physical signal going to the field, milliamp signal or a voltage signal. But since we are using simulators here, we don't have physical analog signals. So I'm just using a D there. Right. If you want to, you can also configure the upper limit and lower limit of your output. So why is this important? This is important if your analog card, for instance, has a resolution of 0 to 8,000, a PLC value resolution of 0 to 8,000, or 0 to 16,000, or 0 to 4,000. So you can change that accordingly. Okay, so you don't have to include a scaling block, something like that. So let's say I'm gonna put the output upper limit here. So we don't want this PLC to go over, let's say, the output analog signal to go over 16,000 or 30,000 or whatever you want it to be. Put it there. And your output limit will be now, we'll look at the addresses now. We'll just put in the variables. And then you'll also have the output lower limit. So if you don't want the output to go to negative. So let's say your VFD does not do reverse. It's only forward actually. Okay, so we only go into reverse. So I'm just going to put the lower limit there. This will also be a word. Right. Then we have to look at your sampling time. So how fast will your PLC sample this information? Yeah, so this is also user defined. Okay. And then we'll look at your operation setting time, the operation setting. So what is this? So this is where we decide whether it's a reverse control action or a forward control action. Okay, so this will also be user defined. Another use for this operation setting will be another function of operation setting will be to use for auto tuning. That's what we'll look at next time. Okay. Then we've got your input filter constants. This is not for damping purposes and to reduce noise. That. This will also be a word. And then the most important, I will say, or some of the most important signals would be now your gains, PID gain and your D time. So we have your E gain, should be a word. Should be your I gain, should be a word as well. Okay. Put your D gain, your derivative gain. So let's suppose that this system requires aggressive reaction to errors. So I'm just going to include that as well. And then you've got our D time, response time. Okay, so they are included. So the thing about all these word addresses from output limit and so on, they are used in a consecutive sense. So in other words, they follow a specific order. And what order do they follow? Well, it's demonstrated in the presentation here. So this order here. So your first word will be operation setting. Second word will be your input filter constant. Third word will be your proportion gain. So if this is D100, for instance, okay, if this is D100, this would be D101, 102, 106, 124. So it will be consecutive addresses that needs to be used in that order. So let's just add in here. So your setting time will, let's call that one your D100 for argument's sake. And the operation setting, let's call that 101. Then your input filter constant, that will be 302. As long as they're consecutive, this is the key point. It must be consecutive. Okay. And then your PID gains will be 103 all the way to 106. So it will be your 303, 304, 305, 306. Okay. And let's see, so then we also have our set points. Those ones are not included there. And then your upper and lower limits. So if you look back at the presentation, upper lower limits, you're looking at 22 and 23. So we go back to the PLC program. So they will be D122, D123. Right, so now we've set all our variables. Let's go back to the program. Okay, so let's need to save this project. Very important. Just gonna call this version 3. Obviously, I'll share the program afterwards with all the both the quad program and the presentation and the PLC program afterwards for reference purposes. Right. So how do we get those variables into this PID? Well, for starters, we want to disable and enable this PID block. And this is where EN comes in. So that would be a normal open contact. And what did we say it was? It was PID start, I think. Yeah, PID start. So this input will enable disable PID block. And then we have move blocks. So for each one of those parameters, the gains and so on, we'll use the move blocks and put it inside of this PID. And all of them will be included in your S3 input here. So you can see it's S3 here, and all of these are S3. That's why they have to be consecutive. Okay. Whereas with S1 and S2, you don't have to worry too much about that. So you can use any addresses, no consecutive addresses required. So S1 is your set point, right? So PID set point, and your S2 is your PID process variable. And then your first input for S3 will be what? Sampling time. Or sampling time. So let's do that. So I'm just going to say sampling time. And this must be your D100, I think. Just make sure. Yep, D100. Okay. And then your output, what will be your outputs? Your output will be your manipulate value. This is the signal go to your valve or your VFD or your heater or whatever control you have in the field. But now we need to add all these other values, the gains and the filter constants and upper limits and lower limits, and they will be all added here. So there are two ways to do this. The one way would be your auto tuning, and the simpler way would be user defined. So we've got about 9 inputs that need to go in here. So we're going to need about 9 move blocks. And you'll see that each one of these move blocks have an enabled input. So when this enabled activates, it will move the outputs, move the inputs to the outputs. And when do you want this movement to happen? Well, you don't want to move it necessarily every time a user activates it. You want to move it when the PLC starts up. And what was that address when the PLC starts up? SM400. Okay, so this would be, I think, PLC start. Yeah, no, PLC start. Yeah, this is PLC start, correct? PLC start. This is PID start, and this counts for all of these blocks. So this counts for all of them. So I'm just going to replicate that. Some of them, yeah. Okay, right. So so now we know these blocks were activated in the PLC start. So okay, so we want to set a sampling time, which is this guy, yeah. And then also we want to set the input filter constant. And we want to set the I gain, for instance. So I gain. It's easy if you have. It's easier for the user to have them in order, but it will still work if they're not in order. Doesn't have to be in consecutive order here. As long as your addresses here follows this specific order, you don't have to worry about the order here. obviously. The time. We'll have a upper limit, so it will be my output upper limit. This will be my output lower limit. This will be my D gain. This will be my P gain. There you go. And then the operation setting. Once again, operation setting. Do you want to fine tune your PID block? Do you want to forward control or reverse control it? So that's the operation setting. Play effect. Just need to remove these blocks to try and make it neater. Yeah, the position of these blocks will determine the sequence. Okay. Okay. So for the sampling time, so if you look at your table here, it works in milliseconds, right? So if we want to, just gonna use a round number, every 200 milliseconds, I want to read what the analog says, and then I want that value to be pushed into my PID. Okay. Input filter constant, that will depend on your application, your installation, and so on. You can start with any value and you can adjust it. I'm just going to start with 70. Right. And then I'm going to use an I gain of 100. So why am I using K's here? K means integer in this case. Okay. In bit manipulation, the K means nibble. So okay, each K is a nibble. The nibble is 4 bits, but we don't have to worry about that here. Here we're only looking at integer values. Okay, so that's where the K comes in. Yes, you can use real values as well. There'll be some conversions to be done. But, for simplicity's sake, we don't want to sit here next week. We're just going to use integer values. So that would be my time there, 10 milliseconds for my derivative. And I don't want my output to go higher than, let's say, 32,000. So that's my range, my analog range. I don't want my output to go higher than that. And I don't want my lower limit to go into negative. So okay, 0, that's lower limit. Then my gain will be, so remember what I said, your D gain, if you don't want a very aggressive system, the gain must be relatively lower than your I and your I and P gains. Okay, so like P, I'm going to make K 200. Okay, especially in an area where there's a lot of noise, although there's not a lot of noise in simulator. So don't have to worry too much about that. Then operation settings. So how does this work? This is one point where the users get stuck with. This entire block here is a operation setting, and the bits are mapped onto a word. In SCADA, we call it a marshalling. Okay, so they're mapped on a word. So your first bit represents forward or reverse action. The second bit will be alarms. Okay, your input alarms. This second bit, your third bit will be your output alarms. Then your fourth bit is reserved. Your fifth bit, B4, will be auto tuning, which we'll discuss in the advanced, more in the master PLC level, and so on and so forth. Okay, so we want the control system to look at the lower limits, and we want it to be backward operation. So if my input rises, or my output will be lower. So it will be filling behavior or heating behavior, not draining. So there's a problem here. We've got a word. So how do we put this bits into a word? We use hex, hexadecimal conversion. So if we open a calculator here, okay, and we select the programming calculator, and we're going to put in bits, so it's binary. So the first one will be on. Second one will be off. Third one will be off. Fourth one will be off. Fifth one will be off. Sixth one will be on. The rest will be off. Okay, so it will be 1 0 0 0 0 1. 1001. So what we have there? X21. So we will use the X21 value in our PLC program. So we'll move the X21 into our operation system. So H21. Right. So K integers, H for X. X is for binary bits that's used on a mapped on words. Okay. Right. So next step, save again. Save. Okay. Now let's compile, see if there's any errors. Error in here, so convert, default all. Okay, so to see if there are any errors in the programming, you go to output here, 0 errors, 0 warnings. So theoretically, the programming here is fine. That does not mean the program will work. It means that the program logic is fine. Okay, so we need to test this. As I mentioned, we want to test this with a GXGT Simple Simulator. So what I'll do is I'm just gonna activate my simulator here. So we go to debug simulator, start simulation. Right, so the simulator is running. Let's quickly go to the bot. Just open another instance of GT Designer. Let's wait for it to load. Okay, so new project. We've got simple in this case. Will be IQF PLC, which will communicate to use Ethernet communication, even though it's simulator. Your Ethernet settings, fine. IP addresses, stack layout. Okay, so now we've got an empty project there, and we can just build a very basic, very simple simulator value, just to show how these two simulators are linked, and a very basic setup of how to extract data and write data to your so-called PLC. So I'm just going to give it a heading here. For reality's sake, yeah, the control illustration. So what do we need to set? Okay, so traditionally we need to set a set point. So with a set point here. So the operator will set a set point. Or how full he wants the tank, or what he wants the furnace, what must the system pressure be, and so on. And this will be a value that will be input from the user in the HMI. Okay, so the input value. And can we recall the addresses for the set points? So we go back to the PLC program. Yeah. So the set point will be P2. Yeah. So we'll choose P2 here. Just going to give it a bit of color. It's a green. Make it a bit bigger so everybody can see. Right. Also, we want to see the process variable, right? So you want to see how the plant reacts. So just do that. So this will be your temperature or your flow rate, system pressure, tank level, motor speed, position, anything analog. And the address here, I just want to see what we do in the PLC. Process variable, that was B0. For those who don't have the software, by the way, yeah, this is a licensed software. You will have to get a license for it. But if you want to just to test the software and you want to do some experiments on it and see how it works, there are demo trial versions. I think they each run for 90 days. Downloadable from our website. So I can also provide the links. So just keep that in mind. Okay, so that will be the process variable. Traditionally, the user can't change this process variable. You can't change that. You can only read it. Okay, you can only change the set point. Okay, so just something to keep in mind. However, for the purpose of this demonstration, since we don't have a physical plant, we're gonna put a process variable in here. Intent, it's the actual flow rate or the pressure, just to see how the PID reacts. Right, then how do we see how the PID reacts? That would be your manipulated value variable. Just your output, the MB. And that was, what was the just D4, I think? Yeah, D4. Let's keep it different color. Okay. What else do we need? Okay, so we need to stop and start the PID controller. Because how are we going to stop and start the PID controller? So we need a button. So just use a button here. Stop and start. What was that address there? PLC PID start. It's M100. And we want it to alternate. So when I press it, it must turn on. Press again, it must turn on. Okay, so just keep that in mind. Keep it a different color. PID diagram. For instance. So ideally, we would like to have graphs here and trending and so on, and pie chart and so on, which demonstrates this control system. We'll look at that in the next PID system webinar, an advanced webinar, how to set that up. But for now, just to save time, this is what we're going to use. So I'm just going to run the simulator. Now the simulators will link. Okay, so this will be what you will see under GXGT there. And I suppose this is what we'll see in the PLC side. Just move the simulator again. So see there. Just going to move it somewhere. Okay, now, so let's say we've got a save point of 2000. Okay, because this will be your scaled to be your scaled input coming from your field. Okay, actually this will be your user-defined process variable. That means the tank level, like let's say 2000 liters or 2000 kPa for system pressure and so on, which will be scaled in the PLC to an analog signal in the field. So we don't have to worry about that. And then this will be what we actually see in the plant. Let's say unscaled with 3000. Okay. As we can see, the PID is not reacting at all because the PID is still off. So let's enable the PID. Okay, so just going to see here. So it's not reacting because it's set on reverse control. So if I make this 1,000, the PID should start reacting, and the PID does react. Okay. So if we had this in forward control, it would have reacted if your set point was higher, your set point was lower in the first variable. But it wasn't reacting because you're already the lowest you can be. Your tank is already uh, uh, um, your VST is already running at its maximum to try to keep the pressure, for instance, or your valve is already open to its maximum to try and fill the tank. So that is why it didn't react. So if we now gradually change this value, let's say we change it to 1,500, we'll see that the rate of change of these variables will change dramatically. And let's see here. Okay, now it's dropping again. I'm just going to make it 21. So it seems like it is it reacts very fast, but now you'll see it will react much slower, as you can see, because they're very close to each other. Okay, so it doesn't need to react very aggressively. So if I make this now 2,000, so now there's no steady state error, and you won't need to change the manipulate value because the valve is already now at its optimal position, or the VFT is running at its optimal speed, so that the error can be zero. So yeah, so this is just a simple demonstration. I will save these projects and send it to you. What you can do is you can just send me an email, and then I'll send it to you. I'll also put it in the chat. I'll see if I can upload this chat as well for those who want to download it immediately. Just want to save this. I'm just going to call this demonstration 2. Right, back to the presentation. So yeah, just a couple of abbreviations and acronyms that was used in this webinar. So if there's anything that's unclear, these are the short terms, the acronyms and abbreviations for each of the mathematical variables that we used, as well as the theoretical variables. And okay, so a couple of resources if you want to research this concept a bit deeper. Obviously, right at the top there, the email of you contains all of this information and more. So yeah, this will be a couple of websites you can look at. Okay, so let's look. If there's any questions? Please then. While I wait, I'm just going to see if I can upload those files into the chat. We can share those files then.
Thank you. Thank you very much.
Most welcome. Okay, we've got a question here. Okay, so we are currently running a pump via VSD with a process variable from a pressure transmitter. Yeah, that's correct. And a set point which is running from a SCADA. That is correct. The process variable keeps over and undershooting above and below the set point. So the VSD keeps on accelerating and decelerating to compensate for the error. Is this normal? In the long run, can the acceleration and deceleration have a negative effect on the motor or VFD? Okay, so let's look at it from the motor's perspective first. So when you accelerate the motor, okay, initially, yeah, it's well known, and you guys will know that during the acceleration you pull a lot of current, much more, like sometimes 600% of the normal motor running current. Okay, so what will happen then? Your motor windings will get hot for that small period of time. Remember, this is a small period of time. It's just a startup. Okay, and when it gets hot, your motor windings has got an insulation on each wire in your stator. Okay, if your wire gets too hot, that insulation starts to wear off. It gets damaged. Okay, which means that if that insulation breaks or they call it fails, the arcing can occur, and then your motor is damaged. So your motor lifetime expectancy is indirectly proportional to the temperature of the windings. Now, if your motor accelerates and deaccelerates the whole time to chase a set point, what will happen is your motor will constantly accelerate and decelerate. So therefore, your motor lifetime expectancy reduces dramatically. Okay. As for the VFD, traditionally, what the guys do in industrial plants, they will go one size higher VFD than a motor, so that the VFD never runs on its maximum current threshold in terms of current output, which means that the VFD components can handle the current that's being pulled, which means that the VFD will run cooler, the circuitry. However, also popular, they don't oversize because of the price factor. So they used to right size VFD for the right size motor, which means the VFD in this case will now also run hot because of the components that's currently trying to give that high current output. The high current output will be due to inertia and momentum of the physical pump on the physical motor components and so on. So yeah, it will reduce your lifetime expectancy of your hardware, both your actuator and your controller. So I suppose you want to know about the solutions. Okay, so for the undershooting, for the overshooting, I would recommend that you do one of the following. So you're going to have to use a fine-tuning method. Okay, so if you're using FX5 PLC or IQR PLC, for instance, you can use the auto-tuning function on the PLC. So if we can just go back to the slides here, this will be your method that involves B4 here. This B4 there. Okay, then you can use that to instruct the PLC to find an optimal control system for the quickest stabilization. Okay, that is if you use a Mitsubishi IQF IQR PLC. If you use another vendor, I suppose they will probably have a auto-tuning capability as well. If not, then you're going to have to use a manual auto-tuning method. That would be your, there's a couple of them. The most popular one will be the Ziegler-Nichols method, which is used to do fine-tuning before the PLC's got intelligent enough to do their own auto-tuning. Okay, so the plants use that. If you don't want to go through all that method, because there's a lot of mathematics and calculations that you as a user need to perform. Okay, if you don't want to do that, I can say the following: the two biggest causes for overshooting will be your P gain is too high. Okay, so in other words, your KP value or your case value, depending on the controller you use. So you need to reduce that. Okay, or another reason would be your KD value can be too high. So if your tank level is too small, let's say a small tank level with an oversized pump or a large pipeline with a large valve in there, then your KD is too large. So you have to reduce your KD value. If it's none of the above, so if your KP value is reasonably low, and if the the VFD, the pump is not oversized for the tank level, or if it's a very large tank level or a very large furnace, or you do temperature control, then the last thing you can look at would be if you use the D factor at all. Okay, so if you use the D factor in that system, make sure that there's no noise or electromagnetic induction on that signal. This you can't pick up with a multimeter. If you can pick up this noise on a multimeter, then it's completely useless case. You can't use that signal. But this you can pick up with a oscilloscope or something like that. Okay, so you're gonna have to look at that signal. If you don't have an oscilloscope, I would recommend you look at a shielded wire cable or earthing. If it's already earthed like that, then I would recommend that you reduce the KP and KD value. If you don't come right, my email is here at the bottom of this presentation, and then you can just give me your PLC details and so on, and then we can look at a solution for you. Okay. Any other questions? Let's see in chat here. Okay, I don't see any other questions. If you guys are interested in the sample programs in the presentation and all of these demonstrations here which we have here at CAD files and PLC files, just drop me your emails either via my email below or in the chat here, and I will send you all of the files today. And if you've got questions, you can also email me. We'll take it from there. So just spoiler, if I can say that. Part 3, we will look at fine-tuning and auto-tuning methods. And also we're going to look at structured data types in the PLC for the PID specific, and also how to get your own function block so that you don't have this mess here, all of this faults, all of this. So we're going to look at function block diagram design and structured data types, which is ideal if you have a lot of PID control systems and you don't want a mess like this to do troubleshooting, or you want something neat, not so many blocks, you want one block. So this will be on the last level, part 3. Right. I can see no questions. Okay, I see an email address there, so I'll send you. Right. Thank you, guys. So have a lovely day, and we will let you know about the future webinars. Thank you.
Thanks, Roy.